Hey guys, this is Mr. Bennett, and this is Unit 5. We're going to talk about the periodic table. For video 5-1, specifically, we're talking about how the periodic table came to be. So that means that we're going to talk about the history of the periodic table. The history begins in the mid-1800s, and it turns out at this point in time, only about 70 of the elements that we know today, and we know over 100 elements today, only 70 of those elements had actually been discovered. But scientists had figured out at this point that of those 70 elements, some behaved very much like each other, meaning they had similar properties, and that these similar properties seemed to follow a pattern. It wasn't until a Russian scientist by the name of Dmitri Mendeleev came along that we were able to organize it and figure out what this pattern might be. So Dmitri was able to, or Mendeleev, was able to, first of all, organize it by atomic mass. So you take all the elements, sorted them out by atomic mass. We'd call this average atomic mass today. And then he also took into account physical and, more importantly, chemical properties. So how the elements reacted. Sorting things this way gave rise to what we call today the groups or families, meaning the columns that we see on the periodic table. So Mendeleev is the guy who's responsible for that whole column organization that we see. Now, Mendeleev's periodic table had some good stuff and it had some bad stuff, meaning there were things that scientists liked about his idea and there were things that they did not like. So in terms of what they liked that it was able to predict the properties of elements before they were discovered. Meaning if we look down here at his table, these guys here, 44, 68, 100, later on when these elements were discovered, even 72, the properties that Mendeleev had predicted corresponded exactly with what was determined when they actually did find these elements. So he was basically guessing what the elements would be like before we even knew about them, and he was right. So that's huge. If you can predict the properties of something before you even know anything about it, then that pretty much suggests that you understand what's going on. What it also did was it accounted for that pattern that they had seen, kind of explained how things worked, and then these groups or columns corresponded with elements that behaved in a similar way, chemically. But there was some bad stuff. First of all, the atomic mass increase was not predictable. So what that means is, for instance, we look here at lithium. Lithium is at 7, has a mass of 7. Beryllium has a mass of 9.4. That's a 2.4 increase in mass. But if we look at beryllium and compare that to boron, which is right next door, the increase only goes up by 1.6. And then from boron to carbon is 1, carbon to nitrogen is 2, nitrogen to oxygen goes up by 2 again, oxygen to fluorine goes up by 3. So there's no predictable pattern. And if we go up and down on this, meaning we look starting with hydrogen and go down this way, same deal. There's no predictable pattern. So unpredictability in terms of the atomic mass was a bad thing. The other problem was the table had gaps or empty spots that he could not explain, meaning these gaps could not be undiscovered elements. They were simply just spaces that he couldn't account for. He couldn't figure out what those were there for, or why they existed. That's not good either. So while Mendeleev's chart was good, his table was great at predicting similar patterns and some new elements that hadn't been discovered yet, these questions here had scientists doubting whether his table was really as good as it seemed. So it took pretty much 50 years to get to a point where they could actually sort it out and figure out what was wrong with the periodic table. First of all, we needed Rutherford. Rutherford, we've talked about him in the past, discovered the nucleus. He's the guy who figured out that the nucleus had protons in it, right? They're positive, and that those protons could be described as the atomic number of the element, and that if you knew the atomic number, you could determine what element you were looking at. So Rutherford figured that out, but he didn't quite understand how that fit into the idea of the periodic table. It wasn't until another scientist came along by the name of Moseley, or Moseley, depending on how you pronounce it, 1913, he rearranges the periodic table by the atomic number. So in other words, he figured out that the mass was not the way to go. Instead of organizing by mass, he organizes it by atomic number. It fixes the gaps. Amazing. So he gets rid of one of Mendeleev's questions or problems. The other part is that because we're going by atomic number, basically to get from one element to the next, you simply change the atomic number by 1. So that's perfect again because it means that the atomic number increases at a predictable rate to change the element. However, a new problem or anomaly shows up. So this idea is that when we look at the current periodic table. And you can see this today, it's still there. We'll talk about why later, but for right now, just understand that this anomaly exists. So some elements, even though they increase in atomic number, the atomic mass actually goes down. So if you look at argon on the periodic table and compare it to potassium, the atomic number goes up from argon to potassium, meaning potassium is deeper in the periodic table. However, if you look at the mass of argon, it's actually higher than potassium. So argon has a lower atomic number, but it has a higher atomic mass. This same phenomenon or anomaly shows up when you compare cobalt to nickel and tellurium to iodine. So they weren't quite sure why this existed, so this was a question, but the rest of this being fixed, the gaps and the predictable atomic number, that was enough to get scientists to believe that the periodic table was a great thing. It works. This phenomenon could be answered later. So this is actually what the periodic table is supposed to look like. Here's our group 1, our group 2, and so on. I know there's this weird column right here, just kind of ignore the boron aluminum for right now. Okay. But anyhow, so this is what the periodic table is supposed to look like. However, what we do is we take this section here, what we call the F block, we pull it out, and we separate it down to the bottom. If we do that, this is the periodic table that we see in class every day, right? Laminated and good for us to use. So the organization of that periodic table all came from Mendeleev and Moseley. So if we compare groups and families we've talked about in the past, those are these guys, right? They are the vertical columns on the periodic table. And then the rows or periods are the horizontal groups that were created on the periodic table. And we know that these horizontal groups coordinate with or correspond to energy levels. So this is energy level 1, 2, 3, 4, 5, 6, and 7, right? Basically, they tell you the energy level, or we would call those rows periods. Okay, so last but not least, I know that we've talked about the periodic table in several different ways. We've talked about the groups, we've talked about the periods, we've talked about the blocks, right? In terms of like S, P, D, and F. But there's another way of looking at the periodic table. It turns out if you look at your periodic table, you will see a staircase. It's just kind of a dark line that goes like so. And it turns out that this element right here on top, this is boron. It's right on top of the staircase. And then if you look at these guys here, so you go down to the next step, you look at the element just above and just below, and then you go over one more, you look at the element just above and just below, and in the last step, you're just going to look at the element on top of the step. So that gives us 1, 2, 3, 4, 5, 6 elements total, right? These guys are called the metalloids. Okay? And then it turns out that any element that is to the left or down in the F block, these guys are all called the metals. And then if you go to the right of the metalloids, these are all called the nonmetals. So this is just kind of the new idea that we're going to add on here at the end of the notes, that not only do we have groups and we have periods, but we actually have, and as well as blocks in terms of the electron configuration, but we also have regions of the periodic table. We have a huge section over here where all the metals are found. In between the metals and the nonmetals, we have the metalloids, and then to the right of the metalloids, in this very small section over here, we have the nonmetals. Okay? Make sure that you complete your WISC, answer questions, and we'll see you tomorrow.